Now we want to take a look at Lagrange multipliers. Now just forget that name for the moment, that's what we're going to build up to. Let's just go back to some fundamental properties of level curves and gradients. Okay, if a function g of xy is set equal to 0, what we have then is a level curve of g of xy. That should be very obvious. An example might be x squared plus y squared minus 4 equals 0. That gives you x squared plus y squared equals 4, clearly the equation of a circle of radius 2 centered at the origin. Just as an example of a level curve. Now we could have x squared y plus xy squared plus x cubed over 3 minus y to the 4th over 7 equal 0. And we would then implicitly at least have y as a function of x, have a level curve y versus x. Y might not even be a function of x, but you would still have a level curve. That would be more complicated. You've seen many examples of level curves by this point. Okay, a tangent to the level curve, to the g of xy equals 0, at a point on the curve is what? It's the instantaneous direction of no change in g. If you have a level curve, the value of the function isn't changing as you move along that curve. So at any point of the curve, your direction of motion is in the direction of the tangent vector. Motion in the direction of the tangent vector is motion in the direction of the curve. The value of the function isn't changing on the curve. It follows that the value of the function has 0 instantaneous rate of change at that point on the curve in the direction of the unit tangent. The directional derivative in the direction of the tangent is 0. Del g at a point, the gradient of g, is the instantaneous direction of maximum increase in g. That's a property that's easily enough proven if you understand the gradient and understand directional derivatives. It's the direction of maximum directional derivative. Also, the direction of maximum increase as we move along the curve is perpendicular. Actually, we don't even have to be moving along the curve, but of course we are. At any point, the direction in which a function changes most rapidly is perpendicular to the direction in which it doesn't change. So the instantaneous direction of maximum change is perpendicular to the instantaneous direction of no change. Okay, these four things. We put these four things together into the whole idea of Lagrange multipliers. Now Lagrange multipliers, it's a simple enough process. You can write down a set of simultaneous equations and solve them, and an answer pops out, but you have no idea, if you don't understand these things and how they're put together, why that works. If you don't understand why it works, then you're limited in your ability to apply it and to think through situations where this is the sort of thing you want to do, or to generalize the process in any way. So we want to talk about the real guts of Lagrange multipliers, not the superficial set of procedures, which are complicated enough. It's not insignificant to learn how to calculate everything you need to calculate with Lagrange multipliers. But we want to first, or maybe you already know it, maybe you're looking back. So after learning how to do this, you come back and understand why it works and what it means. Okay, so we're going to go on with this.